Hello and welcome. What did the doctor say when the invisible man called to make an appointment? Tell him I can't see him today. In this video, we're going to tackle the area problem, which means we're going to find the area from a curve to the x-axis. Now, this may seem completely unrelated to the antiderivatives we've been learning about in recent packets. Or is it? Let's turn to the notes to find out. Before we tackle the actual area problem itself, finding the area from a curve to the x-axis, let's start with looking at areas that we know about. For example, the area of a rectangle. If the rectangle has sides L and W, then the area we can calculate. It's just length times width, LW. We know the area of a triangle with base B and height h. The area of that triangle would be 1/2 base times height. And we know the area of a circle with radius r. It's pi r squared. But can we find a more general way to calculate areas? That's going to be our goal. So we're going to start by looking at areas under curves. For example, the curve f of x equals x squared from x equals 0 to x equals 1. What is the area from that curve to the x-axis? Now, since we don't have a formula for this area, it's not one of the shapes that we know about, we're going to use rectangles to estimate the area. Rectangles work. We know how to calculate the areas of rectangles. You just multiply the length times width. So if we can use rectangles to approximate the area of this region that we're interested in, that'll get us one step in the right direction. Now for the heights, for the heights of each of the rectangles, we're going to use the maximum function value on each subinterval. Let's see where that leads us. So again, this is the goal on the left here, which is the area under the curve x squared from x equals 0 to x equals 1. And when we say under the curve, we mean from the curve to the x-axis. That's our goal, is try to find what that area is. But over on the right, we're going to approximate this area using rectangles. Now what we're going to do is we're going to take the interval from 0 to 1 and chop it up into 4 subintervals. So you can see the first subinterval goes from 0 to 0.25, second subinterval goes from 0.25 to 0.5, and then third subinterval is 0.5 to 0.75, and then the fourth subinterval is 0.75 to 1/2. You could actually write each of these as fractions as well. So it'd be 1/4, 1/2, and 3/4 for the fraction versions of those x values that divide the subintervals. Now why are we creating subintervals? Well, because on each subinterval we can raise up a rectangle that approximates the area under the curve on that subinterval. So for example, if we're going to use these maximum function values, we can look at that first subinterval there from 0 to 1/4 and find where the biggest function value is. It looks like it's on the right side here of that subinterval. And we'll use that to determine the height of the rectangle. So what we could do is we could, on that first subinterval, maybe draw a little line segment up and then over and down. So here's our first rectangle. There's our first rectangle. We probably don't need that bottom line there. There's our first rectangle that we're raising up on that first subinterval. And it approximates the area under the curve on that little subinterval. It's not a very good approximation. I mean, it looks like it has more than twice the area that it should have. But at least it's an approximation. Better than a big rectangle up here or one down here. Let's do that same thing on the next subinterval. So we'll pick the biggest function value, which it looks like is again on the right side, because the function values keep getting bigger as you go to the right for this particular function. We're going to plug that into the function, and that's going to give us the height of the next rectangle. That again is approximating the area under the curve for that little subinterval. Then keep doing it for the third and the fourth subintervals. So find where the biggest function value is. And raise up a rectangle. Whoa. I think it's right around here. Easier for me to draw down than up. a ruler, that's what I need. Okay. So there are four rectangles, one rectangle for each subinterval, and we're raising up the rectangles based on what we said here. We're using the maximum function value, which happens to be on the right side because this function is increasing as you getting bigger as you go to the right. So the biggest y values are always on the right side of each subinterval. Okay, well, that's a good picture. Let's go to computing the areas of each of these rectangles, which is why we're using rectangles. We said we can find the areas of each of these rectangles using the length times width formula. So our goal again is to get the area of the region, R. R is this region right above the actual area under the curve, and we'll call that A. Well, here A can be approximated by the sum of the areas of all these rectangles. That's at least an approximation. Now, for that, let's look at the first rectangle. The height of that first rectangle, is given by the function value at 1/4. Now, to get the function value, we just take the x value there at 1/4 and we square it, right? Take that x value, we plug it into the function to get the y value. In this case, the function is just x squared. So we're going to have, 1/4 squared. That's the height of that first rectangle. And then we're going to multiply that by the width of this rectangle, which is 1/4. That's 1/4. Let me just label that first one. So this right here is calculating the height of the first rectangle, and then this is the width of the first rectangle. And now we're going to do that with all the other rectangles. We're going to add to that the area of the second rectangle. What's the x value that we're going to plug in to get the height of the second rectangle? So if you said 1/2, then that would be correct. 1/2, going to plug that in, which means plug it into the x squared function, so you'll have a half squared. And then times, what's the width of that rectangle? If you said 1/4, that would be correct. It's 1/4, that's the distance across the subinterval here, is 1/4. You can do a half minus a fourth. Or just note that all of these subintervals have a width of a fourth because we chopped up the interval from 0 to 1 into 4 subintervals. So the width of each of those rectangles will be the width of the subintervals, which are going to be 1/4. Each of these are going to have a width of 1/4. Now to get the height of that third rectangle, we'll take 3/4, plug it into the function. This is what it looks like to plug 3/4 into the function, and then multiply by the width of that third rectangle, which is again 1/4. They all have the same width. And then we'll plug in the x value to give you the height of the last rectangle. So that's 1 squared, and then times 1/4. And if you work out all the fractions, you end up getting 15/32, which is 0.46875. So this gives us an approximation for the area of R. Now, if we really, we're kind of estimating things, just eyeballing it, we could say, well, this is kind of like a triangle, so it's pretty close to a triangle in area. It's a little bit less than the area of the triangle that's made by going from 0, 0 to 1, 1 to 1, 0. And the height of that triangle would be 1. The width of the base of that triangle would be 1. So 1/2 base times height would be a half times 1 times 1, which would be a half, which is 0.5. So now but that's an overestimate, right? The 0.5 is an overestimate because there's a little bit less area actually than the triangle. And that's what we're seeing for our estimation. Is we're seeing that our rectangles are actually giving us some kind of overestimate of the area of the region R, but they're still going to be less than the area of that triangle that we were just talking about. So it looks like we get all this extra area right here above the curve, and the extra area above the curve here and here and here. So all of that's weighing into this approximated area. So it's giving us some approximation that's a little bit above the true area of the region R. So we can summarize this by saying when the heights of the rectangles are determined by the maximum function value on each subinterval, then our area estimation is what's called an upper sum. We're going to use that word to describe this summation here. This is going to be an upper sum. And it always overestimates the true area under the curve. So this is overestimating because, again, the rectangles are above the curve. So their areas are going to add up to something that's bigger than the actual area under the curve. Let's take a look at using the minimum function value. What if we did that instead? So on each subinterval, let's use the minimum function value as the height of the rectangle. So here you have the same kind of picture. We've taken our interval from 0 to 1 and chopped it up into 4 subintervals. So we're going to use 4 rectangles again. We could use more rectangles if we wanted to, and that's kind of where we're headed in the long run. But we'll just stick with 4 for right now. And on that first subinterval, if we use the minimum function value, where the small function values are happening to the left. So on the left side of that subinterval, you have a function value of 0, actually. So the height of that rectangle would just be 0. I'm going to draw that little line right there to represent a rectangle that has height 0. It's just a little line segment. Now in the next subinterval, if we want to figure out where the smallest function value is, again, it's on the left side of that subinterval. Because on the left, the function values are smaller. So we can plug in 0.25, or again 1/4, to get the height of the rectangle there. And for some reason I'm using orange. Oh well. Alright, let me just for a moment put these in here. So this is 1/4 and 1/2 and 3/4. Just put those in there again. Okay, the third rectangle would look something like this. Here's where the smallest function value is. And then on the fourth subinterval, the fourth rectangle, if we're going to use those minimum function values so that our rectangles are under the curve, it'll look something like that. So now we can approximate the area under the curve, by adding up all of these areas of the rectangles. So we can say for the first rectangle, the x value that we plugged in was x equals 0. And you get a height of 0 for that one. The widths are still going to be the same. It's 1/4, just like it was before, because we've chopped up the interval into 4 subintervals. So you take the interval length, which is 1, and you divide it by 4, and that gives you this the subinterval widths. Now the next rectangle is going to have an x value of 1/4 plugged in to get the height of its rectangle. So that'll be 1/4 squared times the width of 1/4. The next one will have 1/2 plugged in. And then the next one will have 3/4 plugged in. So each of these are a computation of the area of these rectangles. Now if you work the fractions out, you get 7/32, which is 0.21875. And that's going to give us an underestimate, because all the rectangles are under the curve, and there's some area right here, and right here, and right here, and right here that we're not covering, we're not factoring into our computation. So when the heights of the rectangles are determined by the minimum function value on each subinterval, our area estimate is a lower sum. That's what it's called. And it always underestimates the true area under the curve. So we have like an upper estimate and a lower estimate. Let's see if we can do better. Let's try using midpoints. Midpoints. This is the key right here. We're going to use midpoints to get the heights of each of the rectangles. Well, first off, let's see. We have 1/4, 1/2, and 3/4. Well, what does a midpoint look like on the first subinterval? So from the first subinterval, it's from 0 to 1/4. What does a midpoint look like there? What would be the midpoint of that first subinterval? Well, if you said 1/8, that would be correct. 1/8. You can just take the average of these two. So take 0 plus 1/4 and divide by 2, and you get 1/8. There's the midpoint for that first subinterval. And that's the x value we're going to plug in to get the height of that first rectangle. But before we do that, let's get the midpoints of the other subintervals. So the next subinterval is from 1/4 to 1/2. Can you get the midpoint for that one? If you said 3/8, that's correct. There are a couple of ways we can get that. We can either take the 1/4 plus 1/2 and divide it by 2. That would give you 3/8. Or you can think the spacing between these midpoints is the same as the spacing between the x values of the subintervals. So the spacing between the midpoints will be 1/4, right? To get from one midpoint to the other midpoint, you just go a subinterval distance away. That'll land you in the middle of the next subinterval. And if you add another 1/4, you'll be in the middle of the next subinterval. So you can take 3/8 plus 1/4. 1/4 is like 2/8. And that'll give you 5/8. And then 7/8. Those are the three x values that are in the midpoints of each subinterval. And those are what we're going to use to plug into our function to get the heights of the rectangles. So we're trying to get like a better approximation. So let's plug that into our function. Plug that into our function. And that'll give you the height of that first rectangle. Use green actually there for that one. Okay. Now we're going to plug in the next midpoint into our function to give you the height of that second rectangle. So see how we're plugging in the midpoint to get the height of that second rectangle. These really just go across. Okay, and then we're going to take the next midpoint, plug it into the function to get the height of the third rectangle. And then the last rectangle. Take the midpoint, plug it in. And it gives you the height of the last rectangle. There we go. So we have it visually drawn. Let's do the calculations down below. So we can say that the area is approximately. Now the first subinterval we're plugging in 1/8. If we're using the midpoints, we're plugging in 1/8 into our x squared function. That gives you the height of the rectangle. The widths are the same. They're still 1/4. Each rectangle still fills up a subinterval and it has a width of 1/4. Then we can plug in 3/8. Then 5/8. Then 7/8. I don't know if you can hear the dishes clinking in the background. My wife is working on the dishes right now, and it's an inevitable sound. The kids are asleep, but the dishes still have to be done. All right, so there we get an area approximation using the midpoints of each of the subintervals. And that one, you can tell visually this is going to be a better approximation in this particular case. Because if you look at, let's take the third rectangle, for example. There's a little bit of extra area that we're covering on the left side of the rectangle that's above the curve that we shouldn't be counting. But then there's a little area that we should be counting that we haven't counted. So you can almost take this extra area and fill it into this little area over here, and that would make it for a very good approximation. Now the curve is not a straight line, so it doesn't quite fit in perfectly because it's bending outward here, but then inward here instead of like a perfect triangle. So we're still going to get a little bit of extra area, it looks like. But then the curve is also rising faster, so it's kind of hard to tell. The height is going to be different for each of these. So it's hard to tell if we have an overestimate or an underestimate for this example. But it's going to be a very good estimate, better than the previous two. And you can tell it's in the middle of the upper sum and the lower sum. It's in the middle of those two approximations. So thanks so much for watching, and I'll see you in the next video.